Hello, statistics students. Today we're going to talk about experimental design. We're going to talk about a few different ways of gathering data, one of which is to conduct an experiment. And then we're going to learn how to design experiments so that we can gather data or get our random samples so that our data hopefully will be representative of the population that we're studying. So let's get started. As I mentioned, there are three ways we might gather data. The first method is an observational study. Now, in an observational study, you observe and record, but you do not influence. For instance, I'm trying to determine, on average, how many cars a day drive down the street in front of my school. Well, I park a chair out there and I count every car that drives by. And I do that on Monday, and I do that on Tuesday, and I do that on Wednesday. And I can keep doing that and, until I can get a large amount of data. And then I can average that and say, all right, so the average number of cars going down American River Drive is this many. That would be an observational study. I'm observing how many cars go by. I'm counting and recording, but I am not influencing. Now, some people consider a survey to be a type of observational study. Others consider it separate. I consider it separate. So in a survey, you just ask questions and get responses. Sometimes those numbers can be, sometimes those responses can be numbers, sometimes they can be words, but in general, we're just asking questions and recording the responses. That's a survey. Alrighty, a brief interruption there, not a problem. So far we've discussed an observational study where you observe and record, but you do not interfere. We've talked about a survey where you ask questions, could be verbal, could be written, could be online. The one that we're going to spend a lot of time on today is an experiment. And in an experiment, the researcher influences the results by applying a treatment. Treatment is the key word. Write that down, you're going to need it. So the researcher applies a treatment. And let's go back to sharing my screen with you. And I'm not even sure which. I hope you're seeing the experiment screen. Alrighty, so our researcher is going to influence the results by applying a treatment. An example might be, I'm curious if a quiet classroom or a classroom with rock music or a classroom with country music or a classroom with rap music, which one's going to make students perform better on a test or a quiz? So what I might do is I randomly separate students into groups, and I'd give this group a quiz or a test in a quiet room. And next group might get the country music. The next group might get the rap music. Anyway, you get the idea. The different types of music are the treatments that I, as the experimenter, would be applying. And okay, crazy things on Zoom. Not sure if it's working or not all the time. So let's talk about how to design an experiment. Try to put this to make sure my picture doesn't block anything. So in an experiment, you often have a control group and treatment groups. In my experiment earlier at the music, the no music might be the control group. That's what you want to see. That's like your baseline group. Then everybody else is measured from that baseline. And in the control group, no treatment is applied. Sometimes we apply a fake treatment and that's called a placebo, but it's still considered a treatment. Even though I say no treatment is applied, no treatment is a treatment in experimental design. And what you might do is, if you're a drug company and you want to see if your headache medicine is doing great, is going to cut back on headaches, you might give some people sugar pill or a salt pill. They think you're giving them actual medication, but you're not. Because if they think it, and their headache still goes away, then it's not the medication that's causing the improvement. It's their kind of their psychological belief. So you have the placebo group, and then maybe a 5 milligram version of your drug, and then the other group gets a 10 milligram version of your drug. So you've got 3 treatments. One is a placebo, which is a fake treatment, and the other 2 are different levels of the drug. The objects you're testing on are your experimental units. If they're people, we call them subjects. So in my music example, my students would be the subjects. If I'm trying to see which type of plant food makes the roses grow biggest, so I got this plant food goes to these roses, this plant food goes to these roses, this plant food goes to those, then the roses aren't subjects, they're experimental units. Now here are some more definitions that you need to know. So I'll give you a moment to write those down. So our first definition that we need to know is a confounding variable. And a confounding variable, it's found on page 19 of your textbook, is a variable that confounds your experiment. It causes the experimenter to not to know if the factors that you've affected in your treatments are what's causing the differences in outcome. And a quick example might be, well, if I'm plotting my personal favorite, how many home invasion robberies we get in an area versus ice cream sales? Well, there's a confounding variable there. When ice cream sales go up, home invasion robberies go up. When ice cream sales go down, home invasion robberies go down. Does that mean they're related? No, there's a confounding variable. One of those isn't causing the other. The temperature outside is affecting both of them. When the temperature outside goes up, then ice cream sales go up. When the temperature outside goes up in the summertime, it's not miserable to be outside at 2 in the morning, home invasion robberies go up. So that's a confounding variable. The placebo effect I've already described for you. Let's see if I can find what page it's on in your book. Well, there's a placebo on page 17. The placebo effect is simply, if you give people a placebo, a fake treatment that shouldn't really do anything, like I mentioned, the sugar pill for the headache medicine, many times their symptoms will go away just because they think they're getting a treatment. That's called the placebo effect. Blinding, if you have blinding in an experiment, that means that the patients don't know which treatment they're getting. So if I'm taking the headache medicine, I don't know if I'm getting the placebo, the 5 milligrams, or the 10 milligram treatment. Double blinding is really good. That's kind of like the gold standard in experimental design. Listen carefully. You will need to be able to explain this later. Double blinding means neither the person administering the treatment nor the person receiving the treatment knows which treatment they're getting. Let me explain. let's say I, work for Pfizer, one of these drug companies, and we're testing the headache medicine. So what I would do is I would have a placebo group, a 5 milligram group, and a 10 milligram group. And I would not be the person who administers the treatment. I'm running the overall experiment. I have a doctor who's going to administer the drugs to the patients for me. I tell the doctor, give this to group A, give this one to group B, give this one to group C. The doctor doesn't know which treatment group A is getting. He knows they're getting this one, but is this the placebo? Is it the 5 milligram or the 10 milligram? And the reason for that is we don't want the doctor to even subconsciously let people know what treatment they're getting. Like if he knows that this group is the placebo group, he might say, all right, well, here's your medication, let's hope for the best. Indicating that, maybe they're in the placebo group. Or he might go to the 10 milligram group and go, all right, folks, you should really be feeling better today. Here you go. We don't want them to know. So I'm running the experiment, but the person administering the treatment, who is the doctor, does not know which treatment each group is getting. So again, in a double-blind experiment, neither the person administering the treatment nor the person receiving the treatment knows which treatment is being given. Then we have randomization and replication. And I'm trying to find those in your book here. In randomization, what we're looking for is you want people randomly assigned to treatment groups. If you're testing different weight loss things, weight loss supplements or pills or whatever, you don't want all the super obese people in one group unless that's your treatment. You don't want all the women in one group and men in another. You want to randomly assign people to these groups. Randomization helps prevent bias from creeping into our experimental results. And then replication, I did find that in the book. Replication is covered on page 20. Your experiment doesn't mean anything if you get those results and somebody else does the exact same experiment and gets entirely different results. So you want to design your experiment in such a way that somebody else could replicate it to confirm that your results are accurate. So we want to be able to replicate the experiment and hopefully replicate the results that you got from your experiment. We have a bunch of other definitions. A simple random sample, an SRS. Simple random sample. Here's the way it works. Let's say that I work in the Jelly Belly factory. And what you do to do a simple random sample is everything that you're might possibly, let me rephrase, the population from which you're going to draw your sample, you number everything. So I'd have to number all the Jelly Bellies. Then what you do is you either use a table or even this calculator can generate random numbers. And you generate the random numbers and then pull those samples out of the population. So a better example might be here at school. I would if I needed to pick 25 students randomly, I would number all 2,000 students in the school from 1 to 2,000. And I'd generate some random numbers. I might get number 27. So I'd go on my list. All right, number 27, I'm going to work with that student. Number 200, all right, and work with that one. So simple random sample has two parts. You number everything in the population, then you randomly select numbers and choose those from your population. When you stratify, I ought to keep the book over here. When we stratify, What we do is we create an extra level between the population and the experiment. So in a stratified sample, you first break after you get your sample, you break your sample into groups that are important to your experiment. For instance, if I'm doing an experiment on how fast students grow in high school, maybe I don't want the average that all students grow. Maybe I'm curious, do the freshmen grow faster than the seniors? So in a stratified sample, I would take my sample, I would split it up into freshmen, sophomore, juniors, and seniors. And then each of those 4 groups would get my treatments. Maybe one treatment would be, you know, these kids can only eat this food and these kids can only eat this food. You know, these kids take vitamins. Those would be my treatments. So each of my strata would be, would get all the treatments. So when we stratify, your strata have to be related somehow to your experiment. If my experiment has to do with my experiment just has to do with headache medication, I doubt there's a difference between freshmen and seniors on that. So it wouldn't make any sense to test the headache medication on those 4 groups. But because some freshmen haven't even gone through puberty yet, you know, they might hit that growth spurt and grow, whereas most people are as tall as they're going to be by their senior year. So if I'm measuring growth, obviously the age would matter. So that's a stratified sample, and I'll show you pictures of these in a bit. There's cluster, systematic, and multi-stage, and you should be familiar with those. They are described on pages 22 and 23 of your textbook. Please read those. We'll discuss them, but we aren't going to be too detailed about, we aren't going to spend a lot of time on cluster, systematic, and multi-stage. In class the other day, I talked about an example of a systematic sample, and that was when we stood out in front of the Capitol and every 15 women, we stopped them and measured their height, or every 15 men, depending on which class you were in. You know, I stopped them. By making it every 15th one, that was a systematic sample. So now let's go back to our experimental design, and let's talk about randomized design. Randomized is completely randomized, so it's not stratified. You don't break them up into freshman, sophomore, junior, senior, or you don't break groups up into men, women, and children, or whatever it is you need to study. It's just you completely randomly assign people to treatment groups. There's something called a block design, which we're going to look at, and then also matched pairs. So here are 3 examples of randomized experimental design. And let's take a look at some pictures. Here's an example of completely randomized design. Yes, I would ask you on a test or quiz, it's possible I would ask you to draw a diagram like this. So you start with your subjects, and you randomly assign your subjects to different groups. So label your groups. Now, group 1 gets treatment 1. Don't go subjects gets treatment 1, subjects go straight to treatment 2, and subjects go straight to treatment 3. Otherwise, it looks like your subjects are getting, all of your subjects are getting all 3 treatments. We don't want that. So your subjects get assigned to the 3 groups. Each group gets a different treatment. And then, of course, the important part, you got to compare the results. There's no benefit in doing this if you're not going to compare the results of the different treatments. So this is a diagram of a completely randomized design with 3 treatments. Here is a block design, a diagram for block design. You block your subjects into blocks that have some relation to your experiment. So this is like that stratified sampling. You do that in block design. So let's say that we're testing something and we expect the results to be different for men, women, and children. We would split our subjects up into these 3 blocks, and then we would take each block and assign all the treatments to it. So you'll notice that the men get grouped into group 1, 2, and 3. Don't reuse 1, 2, and 3 down here for the women because they're different groups. So that should be groups 4, 5, and 6. Here we have groups 7, 8, and 9. And you'll notice that the men are all assigned, they get treatment 1, 2, and 3. The women also get treatments 1, 2, and 3. And the children get treatments 1, 2, and 3. So if you were to look at just this part of the experiment, this is completely randomized. But we've added this extra step here. So our subjects are over here. We have this extra step in the between that creates these blocks. And then we assign all the treatments to each block. So this is a block design. This diagram here is a block design, block experiment design with 3 blocks and 3 treatments. And then, of course, we want to compare the results. Now, if you only have 2 treatments, you might consider matched pairs. The first way to do matched pairs is you match your subjects in ways that are to where they're equal to whatever it is you're studying. For instance, I want to know whether this way of teaching a topic or this way of teaching a topic is going to give better results. So what I might do is I would take my students and I would put them in order from highest grade to lowest grade. Then the top 2 students, because they should be pretty matched academically, I assign 1 to one group and then 1 to the other. So I've matched them because they should be relatively equal to each other in academic ability. And so I've made the pair, and then I split. 1 goes to each treatment. Then I take students 3 and 4. I would say that they're matched because their grades are probably fairly similar. Assign 1 to one treatment, 1 to the other. So you could take your subjects, match them, and separate them into 2 groups. So obviously, for matched pairs like this, you have to have an even number of people, and they have to be, you have to be able to match them in pairs, like they're roughly equal, so that your 2 groups they should look fairly similar in whatever it is you're measuring. And then group 1 gets treatment 1, group 2 gets treatment 2. The other way to do matched pairs is to say, you're matched to yourself. So let's say I'm curious, how much, on average, how much stronger are right-handed people in their right hand, that gripping strength, how much stronger are right-handed people in their right hand than in their left hand? So what you would do is I would take all of my subjects, and each subject would do both treatments. I'd get one of those little grippy tools that the doctor uses to measure your strength. I'd have everyone measure their right hand, then their left hand. So this was the treatment where I'm measuring the right hand strength. This is the treatment where I'm measuring the left hand strength. And we'd compare the results and see on average how much stronger people are. So that's a matched pairs design. Now, if we're just sampling out of a population, there are some good ways and some bad ways, or I won't put it that way. I'll say there are some methods that are more likely to give you a representative sample and some methods that are more likely to not give you a representative sample. And simple random sample where you number everything and then randomly select numbers, that usually does a pretty good job. Is it possible you'd get an unrepresentative sample? Yes, but bias is not built into this. It could happen, but it's not built in. Stratified sample could work. Again, it might be important to split people up by age or class. So the freshmen might grow percentage-wise more than the seniors. So it might be, if I stratify my sample, I pick 10 freshmen, 10 sophomores, 10 juniors, 10 seniors, or maybe even a proportion. My sample might, stands a pretty good chance of looking like the Rio population as a whole. These other methods that I asked you to read about in the book are also, they could give you good samples. The two that do not, a voluntary response sample, that is when you just put a question out there and you let people come up to you. If you've ever been in the mall and people come up to you with your clipboard and want to ask you questions, they're approaching you. If you put a poll up on the internet, and anybody who comes to your website can take the poll, that's a voluntary response. Anybody who wants to can do it. And generally speaking, the people who do voluntary response samples are the ones who have the most extreme opinions, usually negative. I mean, if you go to a restaurant, think about it for a moment. Do you think most people fill out the comment cards in a restaurant to tell them about good service or about really bad service? See, that's a voluntary response sample. So in general, because you haven't done anything to randomize, and we know from experience that people with strong negative views generally are more likely to do a voluntary response, that doesn't give us a good sample, or it's not, it could give us a perfect one, but probably not. And then a convenience sample. I'm curious about who everyone's going to vote for in the upcoming election, candidate A or candidate B. So I go ask all my friends. That's a convenient sample. You can generate data, but we don't know that your friends are really representative of the country as a whole. So a convenient sample, it's ones where you can get to quickly and easily, but there's no attempt at all to make it representative. That's going to be a bad sampling methodology. So again, there's a clarification for simple random sample. And in a simple random sample, everyone in the population has a chance of being chosen because you've numbered everyone in the population and then you've randomly selected 10 people. So it's 10, your chance of being chosen is 10 out of however big the population is. And yeah, I'm going through this. I assume you know how to pause button if you need more time to write. A stratified sample, you separate your population into strata first, and then you randomly select from the strata, and everyone has a non-zero but not equal chance. Let's say that we have 500 freshmen at school and 300 seniors. Well, if I'm choosing 10 people per class, then the freshmen have a 10 out of 500 or a 1 out of 50th chance of being chosen, but the seniors have a 10 out of 300 chance of being chosen, or 1 out of 30. So everyone has a chance of being chosen in the school, a non-zero chance, but they're not necessarily equal chances when you do a stratified random sample. Want to re-emphasize this. If you remind me in class, because this video is starting to get a bit long, you remind me in class, there's two things I'd like to talk about in class. This way I'll see who's been watching the video. Please ask me first about this 2018 congressional district census. This is an example of a really horrible way to gather data. And we also need to talk about, put these out of the way here, how to read the random number table on page A7 of the textbook we're currently using. So I'm going to end the video here. Please remind me to discuss, again, that congressional district census, the random number table on page A7 of your textbook, and I'll see you later.